Alright, this is the video for Chapter 20, Nuclear Chemistry. We won't be covering all of this chapter, so any sections that are skipped in this video and on the homework won't show up on the next test. If you were able to come to class this week, we spent that time going through the chart here and applying it to balancing nuclear reactions, so some of this will be redundant for some of you. As you may remember from the beginning of your first semester chemistry class, atoms consist of protons, neutrons, and electrons. Protons and neutrons are in the nucleus, and electrons form a cloud around the nucleus. The number of protons in an atom, known as its atomic number, determines the element to which an atom belongs. However, the combined number of protons and neutrons, also known as the mass number, can vary between different atoms of the same element. Atoms with the same number of protons but different numbers of neutrons are known as isotopes. Many elements consist of more than one isotope, and in some cases, some or all of these isotopes are what are called unstable or radioactive isotopes, because they can spontaneously undergo a process called radioactive decay, where a change happens inside the nucleus. This is in contrast to most naturally occurring isotopes, which are stable, meaning that they cannot undergo radioactive decay. Unlike a normal chemical reaction, where we can only rearrange bonds and electrons, a nuclear reaction, like a radioactive decay process, can actually change the contents of the nucleus, and in many cases the type of element itself if that nuclear change causes an increase or decrease in the number of protons. The main types of radioactive decay processes are shown in this chart. The first is alpha emission, where an alpha particle is released. An alpha particle is just a combination of two protons and two neutrons, or a helium-4 nucleus, without any surrounding electrons. The fact that two neutrons and two protons are ejected from the nucleus results in a decrease in the atomic number by 2 and the mass number by 4. By the way, you don't really need to memorize the last three columns of this chart if you remember the fundamental rule of balancing a radioactive decay equation. The sums of the atomic numbers and mass numbers on both sides of the reaction equation need to total the same amount. Moving to the next row, we have beta emission, which is where a radioactive atom releases a very high energy electron known as a beta particle. For purposes of balancing the decay reaction, we can think of a beta particle as having a mass number of 0, since electrons have negligible masses compared to protons and neutrons. And we can think of a beta particle as having an atomic number, in quotation marks, of -1, since electrons are negatively charged. The next entry is gamma emission, where an atom emits a very high energy, very high frequency photon of light, much higher in energy than a photon of visible light or even ultraviolet. Since photons have no mass at all, and don't have any electric charge, a gamma emission on its own doesn't change the atomic or mass numbers. If you're wondering how a gamma emission can result in any nuclear reaction at all, it's because gamma emissions don't usually happen on their own, but instead alongside some other type of nuclear reaction. The next type of decay is known as positron emission. A positron is actually an antimatter particle that has the same characteristics as an electron, but with a positive charge instead of a negative charge. So it effectively has a mass number of 0 still, but a quote-unquote atomic number of +1. Because a positron is just an anti-electron, it's sometimes known as a beta plus particle. Interesting side note, if you ever have a medical scan known as a PET scan, it works by tracking the distribution of positron-emitting radioactive isotopes in your body, so the tracer they inject you with literally contains antimatter. Fun. And lastly, we have electron capture. This has the same effect on a radioactive nucleus as a positron emission, but occurs via a different mechanism. Instead of emitting a particle, the nucleus captures one of the atom's inner electrons and uses it to transform the nucleus. This is one of those decay processes that typically involves the release of gamma-ray photon at the same time. If we look at the stability patterns of isotopes, we can see that as the atomic number increases, so does the neutron count of the isotope stable enough to be detected. The neutron count increases faster than a 1-to-1 rate, which is why elements with low atomic numbers like helium, carbon, nitrogen, and other examples have atomic weights roughly double that of their atomic number, but the same is not true for higher atomic number elements. Many naturally occurring radioactive isotopes are part of what are called decay chains, where a radioactive isotope decays into another radioactive isotope, which decays into another radioactive isotope, and so on, until the process eventually results in a stable isotope. Here we see an example that includes the important radioactive isotope uranium-235, which over time undergoes a series of alpha and beta emissions until, eventually, the process stops at lead-207, which is a stable isotope of lead. Now, the process of radioactive decay happens on wildly different timescales, even within the same decay chain. This brings us to the reason why we're covering this content at the same time as chemical kinetics. One of the most important parts of nuclear reactions are their decay rates. If we monitor the decay rate of any radioactive nucleus, in this example phosphorus-32, we'll observe that the half-life stays constant. For P32, this half-life is 14.26 days, meaning that after 14.26 days, only half of the P32 nuclei initially present in a sample will still be present. After another 14.26 days, you'll have only 1/4 of the original amount. After a further 14.26 days, only 1/8, etc. As we know from chemical kinetics, assuming you watched those videos before this one, the constant half-life implies that radioactive decay is a first-order reaction, and indeed, this is the case for all known radioactive nuclei. This also means that the half-life is related to the rate constant by the formula half-life equals the natural log of 2 over the rate constant, or approximately 0.693 over the rate constant. This nature of half-life isn't just some random fact about radioactivity. It actually is important for a lot of purposes. One such purpose is calculating the age of some object based on the amounts of certain radioactive isotopes present. Probably the most famous isotope used for this purpose is carbon-14 in carbon-14 dating. Carbon-14 is a radioactive isotope generated in the atmosphere when nitrogen-14 atoms are bombarded by neutrons from space. The process by which that occurs is shown here. The carbon-14 thus formed goes on to bond with oxygen, forming carbon dioxide via natural atmospheric processes. Carbon dioxide containing carbon-14 still has essentially the same chemical properties as regular carbon dioxide, so it eventually enters the food chain where it gets taken up by plants via photosynthesis. Organisms that eat these plants will then contain some of the carbon-14 the plant absorbed. Carbon-14 has a half-life of around 5,700 years, beta decaying into nitrogen-14. By measuring the ratio of carbon-14 to other isotopes of carbon, the major one being non-radioactive carbon-12, it's possible to determine how long ago an organism died, in other words, when it stopped being part of the food chain. The less carbon-14 present, the more half-lives have passed, and so the older the organism. Other radioactive isotopes can be used in other radioactive dating techniques. For instance, potassium-40, a naturally occurring radioactive isotope of potassium with a half-life of around 1.3 billion years, can be used to determine geologic ages of rocks. And yes, since potassium-40 is a naturally occurring isotope of potassium, bananas are slightly radioactive. In fact, potassium is present in all of our cells, and so we ourselves as humans are also slightly radioactive. And fun side note, the half-life of uranium isotopes, U-235 and U-238, is actually how we know the age of the Earth, which is around 4.5 billion years old. All that's to say that the first-order kinetics and half-life of radioactive isotopes are useful.